Okay. Let's get started. We're in lecture 10. This is going to be our last lecture on just truss analysis, where we're going to have coverage of the method of sections. That isn't to say that's the last time that we're going to do truss analysis in the class, because we'll do it again. We're actually going to be doing it next week, but we're doing it for a different purpose. These last couple of lectures, the purpose has been solely to determine the internal forces inside the truss elements. Well, our next topic is going to be looking at the structure and assessing how much it deforms under an applied load. So what I'll say is Friday is going to be an interesting lecture because it's going to be a little bit like movie time, and it's going to be different than everything we've done up until now. So because we're going to go through a little bit of theory and a little bit of background, but I do have a reference to Mario and Link in my slides on Friday, so fun stuff. Okay, homework 3.2 is still being graded, but 3.1 is graded, and everything before that's graded. Attendance is up to date. 3.3 is due today. I've got 3.4, which is going to be our sections homework. What I'll say about, not this one, but the next one. So the homework that's assigned today is due Friday. I'm going to assign a homework Friday. It is not due Monday. It is due Wednesday, okay? Simply because it's not that the homework is much longer, but it's going to take a little bit longer in class to get through that assignment. So homework 4, instead of it being assigned Friday due Monday, it's assigned Friday due Wednesday, okay? Everybody with me so far? Okay, any questions on bookkeeping? Don't forget we have our exam review, not Friday, but next Friday, and then we have our celebration of learning Monday the 25th. So, sound good? All right, okay. So today what we're going to do is we're going to close out our discussion on the analysis of trusses, looking at the method of sections. What was that? Okay, so in our last couple of lectures, what we've been doing is we've been looking at plane trusses, and I always like to go back and make sure that we're all aware of our assumptions when we're analyzing trusses, and that is that all the members are connected by frictionless joints, which basically means there's no unintended or unaccounted for forces besides the ones that we directly can see with our free body diagram. No need to account for friction or anything like that. We have loads applied only at the joints, and we have centroidal. We have our joints configured such that all the centroidal axes of each members all coincide to a singular point. So what that means is that each member is an axial force member. It only contains an axial force, either in compression, tension, or it might contain zero force, as we've learned in the past couple of lectures. Now, we have discussed that there are two methods for analyzing a truss, and we spent most of our time analyzing trusses using the method of joints. It is tedious. I think if some of you did the whole truss on the homework, you know what I mean. It's a little tedious. But it works in terms of solving the entire structure, which is why I spend most of the time in structural analysis focusing on the method of joints. But I do like to cover the method of sections because it can serve as a gut check, if you will. So what is the method of sections? I mean, you can probably sort of discern what it is by its name, but the idea is that with the method of sections, what you're doing is you're taking the truss. And remember, we break out our secret weapon of structural engineering, the samurai sword or the lightsaber if you're a sci-fi fan, and we cut the truss in two, okay? And the idea is we had a singular truss with a singular free body diagram. Now we split it into two trusses, or two sections of a truss, and each one of those chunks of truss has its own free body diagram. And the idea is that if the entire truss is in equilibrium, then either section is in equilibrium. And so that's what we mean when we apply the method of sections. Now, one of the advantages of the method of sections is the fact that when we looked at joints, because of our assumptions, joints are considered concurrent force systems, which means all the forces at a joint all meet at a common location. So whenever you're looking at joints, you can only assess joints that have two unknowns because you don't have that third equation of equilibrium handy. You can only apply the sum of the forces in the x direction and the sum of the forces in the y direction. That's not the case with the truss section. With the truss section, you're dealing with a non-concurrent force system. So you have forces applied to what's assumed to be a rigid body all over the place. So now that segment of truss must satisfy moment equilibrium as well. So you've got three equations of equilibrium that you can apply. So what that means is whenever you're applying the method of sections, you can cut a section through any point in the structure, but it can only contain at most 3 unknowns, okay? So with truss joints, when we were looking at the truss, we had to analyze joints that had at most 2 unknowns. Now with the method of sections, we can look at sections that have 3 unknowns because we have that additional equation of equilibrium. Now, the other thing I want to mention about the method of sections is a little bit about practicality. So going back to, and I mentioned this example pretty early in the semester, but the idea is if I'm sitting here at this table, okay, if I'm sitting here on this table, and Elaine has a samurai sword or a lightsaber, she's a sci-fi fan, she cuts to the table, I fall to the ground, okay? The reason why is because I have removed from the structure the ability to resist those internal forces here. Now the thing is, those internal forces are the same at this point in the structure, whether you look at this side of the table or this side of the table. So whenever you're applying the method of sections, it really doesn't matter which side of the truss that you look at. So I've got an image here of a pretty straightforward truss, and let's say I'm cutting this section here. I can cut a section and look to the left, or I can cut a section and look to the right. Analytically, it doesn't matter. You're going to get the same answer as long as you do the math correctly. But just because there is theoretically no difference doesn't mean there's practically no difference. I don't know about you, but if I cut a section here, I'm probably going to look to the left. There's just less stuff on that side of the section. There's less truss joints, less members, less reactions, less forces. It's just less bookkeeping at the end of the day. Again, I'm all about performing the analysis correctly, but we don't need to make it more difficult than it already is. Okay? Does that make sense? Okay. And what we're going to do today is we're going to look at I want to say a somewhat involved structure, but we're going to look at the method of sections on a fairly involved truss. And so I would say this is probably one of the more involved trusses that we've done this semester. And so what we're going to do is I've got here a problem here, and we're going to determine the internal forces of the following members, CD, CK, and JK, using the method of sections. Now I'm going to break out my highlighter and just show you, let's just sort of highlight which ones those are. So let's see, so we have CD, CK, and JK. Okay, so where are we going to cut a section? Well, through those 3 members, pretty easy, right? Now, there is nothing that says, so let's say if we were solving for this member, and I don't know, this one. We could still cut a section through here, and then, I don't know, maybe apply a method of joints on J to get that one. There's nothing to say we can't do that. I'm just focusing the analysis around these members because I want the section cut to be fairly easy to interpret, okay? So what we're going to do is we're going to take our truss and we're going to samurai sword or lightsaber through here. Okay, and so we'll call this section 1. Okay, and let me ask you all. You tell me. Do you want to cut this section? Would you like to look to the left or would you like to look to the right? What's that? Left. I think looking to the left makes a little more sense. Okay. Now, one thing if we're talking about practical disadvantages, at least when you're first starting out with the method of sections, you got to draw all this stuff all over again. You do, you know, it is what it is. But I mentioned this earlier, a practical advantage. Can anybody think of a potential environment where the method of sections might have an advantage over the method of joints? Something you might be experiencing as a senior? The FE exam. So the FE exam, you might see a truss like this and they're asking for the force in this member, just cut a section. So, okay, so what we're going to do is we're going to redraw the free body diagram, okay? And I'm going to take me a little bit, but I want to do this as accurately as possible. So what we're going to do is we're going to say section 1, 1, and we're going to say looking left. So I'm going to redraw all this, but I'm going to make a note before I draw this, okay? I'm going to say note, all members assumed to be in tension, okay? We're going to assume all members to be in tension so that if we get a negative answer, we know our member is going to be in compression. We're just going to let the math do the heavy lifting for us, okay? So let's draw out this free body diagram, okay? And let's take our time with this. So, okay. So here's what I'm going to do. All right, so I've got, put a joint here, put a joint here, put a here, and a joint here, put a joint there, put one about like that, and maybe one about like that. Okay, so we'll call this, remember, now one thing I'll say, if you're doing this by hand, try and bring a straight edge, because I'm telling you, it makes your life a lot easier. Okay? Now, what I'm going to do at this point, so I've cut the section right here. So here's the truss, and it's sort of going like this, right? And so I cut a section, like this is where I cut the section. I cut the section right here. Okay? What I'm going to do is I'm going to sort of like draw these dashed lines. The idea is that I am only considering the equilibrium to the left of the section. But I want to have maybe just like an idea of what the truss looks like on the other side. Because I'm going to reference those joint designations here in a bit. Speaking of, let's write those joint designations. So I have joint A, joint B, joint C. This is joint D. This is joint K, J, on joint I. Okay. I just wanted that there for the sake of discussion. Okay. And so the idea is we cut our section. This is us cutting the section. So we cut the section like that. Okay. So let's go ahead and identify our unknowns. Okay. So we have an unknown force down here. We'll call that CD. Okay. And for our diagonals, what I'm going to do is I'm going to say, let's call this, so we'll call this CKY. CKX. JKY, JKX. And let's go ahead and put those slope ratios on there. So we've got the slope ratios from up here. So it's a 1-to-1. And this is a 1-to-6. Okay? With me so far? Okay. Now let's draw our applied loads. So we have a 20 kip load right here. We have a, bless you, 20 kip load right here. And a 45 kip load right here. Okay. And the only other thing I'm going to do is put some dimensions on here. So each one of these segments here is 30 feet. Okay. And let's look at our dimensions up and down. So the dimension from A to I, 15 feet. This one is, I believe, 10 feet. Can anybody tell me what's that dimension from J to K? Like, what is this dimension right here? What's that dimension? Anybody get that?
5 feet.
5 feet, okay, 5 feet. So that makes this total height 30. So you can see, like, for example, this diagonal member right here, it went over 30 feet, it went up 30 feet. So that's why it's at that 1-to-1 slope ratio. Which, one thing maybe I glossed over, I want to make sure, is everybody comfortable with this notation right here? That notation where it says 6 at 30 equals 180. Is everybody, you know what I mean by that? So if you've got, bless you, if you've got the truss down here, so the entire truss is 180 feet long, and each of those gaps, there's 6 of them, and they're 30 feet long. So I think I might have had a couple problems where I just threw that up there. I wanted to make sure that was clear. I'm getting the feeling y'all saw that in like 102 or something like that. Am I right? Okay. All right. Now I know that's a lot of drawing, so I'm going to give everybody a sec to catch up, and then we got to talk strategy on how we're actually going to assess this. I honestly think this is the hardest part. This is the hardest part. Just getting all your dimensions redrawn, getting all that figured out. You know, I think that's the most difficult part. So I'll give everybody a minute on this. Okay. Is everybody good, or do y'all need a minute? Okay, because we got time today. We got time to handle this. Okay. So the first thing I want to do is I want to look at this like it's a joint problem and start to illustrate why we're using the method of sections. So let's go back to our goal. We're trying to solve for these unknowns. That's what we're trying to do. Okay. Could I go ahead and sum forces in the x direction? I mean, I could, but like, what's the problem if I do that? I have 3 unknown components in the x direction. So I could write an equation of equilibrium, but it really wouldn't tell me anything. Like, all it would tell me is that plus that plus that has got to be 0. But it doesn't solve for any one of them, right? So there's no point in doing that right now. So that means I should sum forces in the y direction too. That's what I should do, right? You're shaking your head. No, why? There's 2 unknowns, right? So, okay. All right. So does everybody see that the application of summing forces in the x direction or summing forces in the y direction would really not make sense right now? Okay. That's the whole reason for cutting a section. Remember, what is the advantage of cutting a section? Like, why do we do that? It's so that we can solve for 3 unknowns at the same time. So, but solving for 3 unknowns means we have an additional equation of equilibrium. What is that? Sum of moments. Exactly right. So, whenever we're looking at a section, generally the very first thing that we should be doing is summing moments, right? That's what we should be doing. Okay, so let's talk about summation of moments. All right? Now, whenever we were solving for support reactions, remember when we applied sum of moments, we were kind of choosy about that. We would pick a point about which to sum moments that eliminated a lot of unknowns. Like, we had a simply supported beam, we would say sum moments at the left support so that we could solve for the reaction at the right support, because it eliminated that unknown, because the forces went through that point, right? Okay? So what I'm getting at is we could sum moments like at B if we wanted, but that wouldn't create a friendly equation to solve because we've got a bunch of unknowns and they're not intersecting at that point. So what I'm asking is, if we are going to apply the summation of moments, where should we sum moments? I propose that there are 3 potential locations. All right, and we're going to talk about each of these, and I want to investigate which one makes sense, which one we think is easiest, which one we're going to go with, etc. So can somebody identify a truss joint about which we could sum moments and would eliminate some unknowns? As many unknowns as possible. Joint C, okay? If we summed moments at joint C, what would that eliminate? It would eliminate CD and CK. Is that an option? Yeah, it's an option. So if we summed moments at C, what would we be solving for with this expression? We'd be solving for JK, right? That is an option, okay? Does anybody see another option? Where's another place about which we could sum moments? K. Okay, joint K. Eliminates. All right, so eliminates. What members is that going to eliminate? It's going to eliminate CK and JK. All right. Now I just want to identify the points, and then we'll discuss which one we should use here in a bit. Does anybody see a third point? So let me give you a hint. So this one eliminates CD and CK. This one eliminates CK and JK. So where would we eliminate CD and JK? Where would we do that? Maybe right there. This point, I mean, the structure doesn't care where we sum moments. We can sum moments anywhere. If we wanted, what we could do is we could identify the location out here, and it wouldn't be all that difficult. We could identify the location out here. We could identify the location out here about which we could sum moments. I'll call that, I don't know, I'll make up a name. We'll call that point X. I could sum moments about point X, and that would eliminate those two diagonals. Does everybody see that those are three potential options? Now, which one should we use? Okay? I want to look at this second option. Okay, I like being strategic. I want to make sure that we are applying logic to our scenario. So let's conceptualize in our head. Let's use our noggin for a bit. When we sum moments at K, if we sum moments here, what member are we going to solve for? CD. CD. What are we going to be left with after that?
Still have two unknowns in the y direction.
And two unknowns. We have two diagonal unknowns. Break out the 2 by 2 equation solver, right? Do everything we did on the last one work all over again. Do you see what I mean? So if we were to apply option 2, would it work? Yeah, it would work, but it would probably lead to more computations at the end of the day because we're going to have two diagonals left over. Does everybody see that? So I'm going to put a big old frowny face on that one. Okay? I'm putting a big old frowny face because I think it's going to result in a lot of work. Okay? option 1. Okay, option 1, so if I apply option 1, I sum moments at C, okay, I'm going to solve for this diagonal. Once I solve for this diagonal, what am I left with? I'm left with this. 2 horizontals, 1 vertical. Then I can apply sum of forces in the y direction to get that, slope ratio to get that, sum of forces in the x direction to get that. A lot more direct. Does everybody see that? So it's easier. It's easier. I'm going to put a little happy smiley face on this one. Those are very technical engineering symbols, by the way. That's very important, the terminology. Now, I would argue that summing forces in the x direction, summing moments at x would also lead to the same amount of computations here and here. But because the point is off the truss, there's a few more dimensions that we have to figure out. So maybe what I'll do is I'll say, it works, but it's probably not as advantageous as to just sum moments at C. So do we all agree that summing moments at C is the one we ought to do? Oh, okay. And I go through this stuff because I think the math is easy, but you're going to be given a truss and being told to solve for these forces. Nobody's going to tell you how to solve it. So I want you to kind of think through about, okay, if I do this, this is what it's going to leave me with at the end of the day. So I want to make sure that I'm applying a strategy that's as advantageous as possible. Okay, oop, I didn't mean to scroll there. All right, so let's sum moments at C. Okay, so we're summing moments at C. All right. Now, before we handle this JK and JKX and JKY, I want to deal with the applied loads first. Okay, so we're summing moments at C. Let's just take each of the loads left to right. Does the load at A generate moment at C? Yes. Does it belong on the left side or the right side?
Left side.
Left side. And what's my moment arm? 60 feet. I heard a couple of people say that, and that's correct. What about this 20 kip load? Okay, 20 kips. Does it generate moment at C? Left side or right side? And moment arm? 30 feet. What about this 20 kip load? Do we consider that? No. What about CD? Do we consider that? No. Okay, what about CKY and CKX? Do we consider that? No. Now let's talk about that. Why? What's that?
The resultant goes through C.
The resultant goes through C, right? Okay. Now let's go back to that. I want to hit the rewind button a little bit. I want to talk about statics, Engineering 213. And I want to talk about a principle that was discussed in that class called the principle of transmissibility. Okay? What is the principle of transmissibility? Okay? Let's say we got a tug of war going on. You've got one end of the rope, I've got one end of the rope. You're pulling 20 pounds that way, I'm pulling 20 pounds this way. Okay? Whether we're 10 feet apart or 100 feet apart, it's the same line of action, right? We're both experiencing the same thing. You're having to hold me back, right? So whether I'm this far away or this far away, the rope is still experiencing 20 pounds in tension. Make sense? So what that means is that you can take components of a load and move it along its line of action, right? So if I have, let's say, a line of action like this, I can put its X and Y components here, I can put its X and Y components here, here, anywhere along that line of action, and it will generate a free body diagram that meets both force and moment equivalency. So I propose that this X and Y component can be slid down to joint C, and they both go through joint C. No moment arm. What about JK? Okay, So if I slide JK, I don't want to reach that far high, so we'll scroll up a little bit. So if I take this and I slide it up and down, I propose I can slide it anywhere along that line of action, anywhere along that blue dashed line here. What if I take that x and y component and I put it at j? Do I have to consider jky? No, but I do have to consider jkx, right? jkx generating clockwise moment at a moment arm of? How far is jkx going to be from C? Hold on. 25. From here to here is 15 and 10, 25, right? This is like the hardest part, is making sure that your diagram is drawn well, because as long as you take the time to do that and put all your dimensions, those errors kind of go away. So we have jkx feet. At this point, this problem is really easy. I promise. So, what do we got? We got jkx times 25 feet plus 45 times 60. Anybody got the Casio FX115S plus or similar scientific calculators? 2700. Now 20 times 30, I can do that one in my head. That's 600. So jkx times 25 feet. 600 minus 2700, what is that? Negative 2100? Divided by 25. Ooh, we got jkx is negative. Negative what?
84.
84. Do I have a second on that?
Yeah.
So 84 kips, and I'm going to draw that way. Ooh. That means we made an incorrect assumption, but it's right here. It's what I'm talking about, right? Just let the math work itself out, okay? All right? Now I'm going to stop being the train driver. I'm going to let you tell me what to do. What do I do?
Slope ratio.
Slope ratio. jkx. So now I can use the slope ratio to get jky. So jkx is to something as jky is to something. What goes here? jkx is to, as jky is to 1. Because it's a 1 to 6 slope ratio. So therefore, if I've got jkx, jky is 1/6 of jkx, which is what?
14.
Say it again?
14.
14 kids. And it's negative 14. So 14 kips, in this case, going down. Make sense? All right. Any questions so far? Now what do? I got 2 more members I got to solve for. What do? Well, tell you what. Some forces in the y direction, not the x direction, because the x direction I still got 2 unknowns. The y direction I've got that. Okay? So, let's handle that. So, let some forces in the y direction. Here I'll the box for a minute, so make sure that's okay. Okay, so what do I got? I got 45 kips going up, 20 kips going down, 20 kips going down. Let's see. Okay. So 45 going up, 20 down, 20 down. Don't have to consider that, consider that. I got CKY going up. All right. Now, did I forget something? JKY. Now I want to show you something, okay, just so you're aware. Okay, here's my free body diagram. Which way do I have JKY pointing? up, right? Now there are two ways I could do this. One way is to say JKY is negative 14 kips over here, or I could say JKY is positive 14 kips over here. Because I know JKY is 14 kips down. However you want to do this, if you want to just put a negative here or a positive here, it doesn't matter, you'll get the same answer. So I'll let you decide how you want to do the bookkeeping. What I'll do is I'll just respect the free body diagram, and I have JKY pointing upwards, but I got a negative answer. Again, I'm just going to let the math do the work for me. So CKY plus, okay, so I got 45 kips minus 14 kips is 40 kips. So CKY plus, what do I have here? I've got 45 and 14, what is that, 31? Did I do that right? Therefore, CKY is plus 9 kips. So 9 kips upwards. Whether you put a negative 14 over here or a positive 14 over there, you get the same answer. Okay? So far so good? Now what? Slope ratio. So if I've got CKY, I can get CKX. And what is the value of CKX going to be? 9 kips. And why is that? 1-to-1 slope ratio. So slope ratio and I think we have that drawn like that. Okay. So what we'll do is since I'm sort of doing this all over the place, we'll say step 1. We'll call this step 2. And then step 3, what's left? All right. And if we sum forces in the x direction, what do we got? So we've got all of our arrows drawn to the right. So we have CD, CKX, which is plus 9 kips, and we have JKX, but that's negative 84 kips. And so there's nothing over here. So 0 equals CD minus, what is that? What's 9 minus 84? Is that negative 75? Did I get that right? Okay, there we go. So therefore, CD is plus 75 kips, or 75 kips to the right. And then the only thing left to do is to just collate our answers, right? So here's our JK. Here's our CK. And here's our CD. So help me out. Remember, CD is going to be experiencing tension or compression? Tension. Because we assumed tension for all of our members, we got a positive answer. So this one's in tension, this one's in, and this one's in compression. Okay, so to summarize the problem, all we got to do, just do this down here. So summary. So CD is 75 kips in tension. So that member's being yanked on. CK is being yanked on, but that's the square root of 9 kips squared plus 9 kips squared. Break out the old Pythagorean theorem. What do we get for that?
12.73.
12.73 kips in tension. And for JK, what are we getting for that? Casio FX 115 ES Plus or similar stuff. All right. Anybody got an answer for me?
85.2.
85.2. I think it's like 1.6.
Yeah.
We'll put it 2, that way they're all at 2. And that, ladies and gentlemen, is our answer. All right. I think that this is a problem that if you were to do it yourself, I mean, we've been doing this problem for about 30 minutes. If you were to do it yourself, it'd probably take 5 or 10. That I think that there is value in taking a little bit of a step back and making sure that we understand the strategy, that we understand the concepts. Any questions? I want to bring something up before we close. Any questions? All right, so I want to make sure we're all on the same page. We're 3.4. Okay, so this problem, you're only to solve for the forces that are indicated. Don't do the whole one. Just the ones indicated. I don't want the homework to be longer than it needs to be. And I've given you the reaction on that side, okay? I'm trying to make it as easy as possible. So it should be a relatively short assignment, okay? Any questions? All right, I'm gonna bring up the code one more time in case anybody missed it. I will see you all on Friday.